So welcome to our second lecture on cloud computing. So today we will look into base technologies for the cloud, so basically computer architecture and accelerators and so on. Before we go into the technical part, I investigated a bit about the exam and I learned that actually Proctorio, that I announced last time, is no longer available at TUM because of the data privacy concerns in the ministry. We had so many requirements and constraints that it did not make sense to continue that, and it's quite expensive, so TUM decided not to continue with the Proctorio. So we still hope that we find a way to do Moodle-based exams. In Proctorio, it was that you are proctored, so your camera and mic and so on were used to actually verify that no one is in the room, that you don't discuss a question with someone and so on. And so this we cannot use and will not use, and so the current plan is to have the Moodle-based exam in the lecture hall. So you will simply use Moodle to fill in a quiz and answer the free text questions. So our current idea is that we could actually ask you to do a screen recording and then find a way to automatically check your screen recording, that you don't go away from the Moodle quiz. But that is to be discussed further, and if this will not work out, we cannot do that. We will probably use TUM exam for our exam. Yeah. Good. So then let's look at the contents of today's lecture, and after the lecturing part we also have the first assignment in the exercises for you, which will be presented by Anshul. So I talk a little bit about all these topics that are relevant for IT and cloud computing, and I will start with a semiconductor process, that you have a little bit of background in that field as well. Then we look into processor architecture, so how is a processor designed for server systems. That is important, obviously, in the cloud. Yeah, these are data centers with servers. And we will also look a little bit what's happening in the mobile segment, what processors are there and what are the features that you get. Then we look at accelerators. That is a topic that many people are very much interested nowadays. And also the cloud providers. We had actually in the first meeting someone asked about quantum computing. So the cloud providers also offer you specialized machines, right, that are specialized in the hardware that they have, maybe even a totally different programming paradigm or execution paradigm. And so they also use up this or support this trend towards accelerators. And so therefore I think it's an important topic here as well. We look a little bit into data centers, and that will fill the time that we have today. There is definitely also to come a bit of a background information about networks and storage. So these two topics I will not be able to cover today. So let's start with the process technology. So process technology means the process that is used to build our chips, right? Fabricate our chips, and you probably are aware that there are these wafers, silicon wafers, that are quite large, can be like that size, right? And then the companies basically replicate the chips over such a wafer, as shown here in the picture, and then they cut them, and then you get these little squares are basically the chips. And the chips are then packaged into plastic or whatever package. There are different connectors for the package for your printed circuit board. So you can have pins, for example, but for the new processors, they have so many I/O connectors that they usually use balls to connect these pins to the printed circuit board. So, you probably also heard about this name of the process. So we have a process which is 45 nanometers, 30 nanometers. Currently it's 10 nanometers or even below that, 7 nanometers. IBM has a process that is called 2 nanometer process. So basically what this means, and these are, I think the terms are not used precisely always in that way, is what is the minimum feature size that you can actually implement on the silicon wafer, right? And so we implement basically transistors, and the classical transistor is a planar transistor, so you basically have here source and drain, and then you have the gate above source and drain, and via the gate you control how many electrons can tunnel from source to drain. Yeah? And in the new processes, so with the trend to get smaller and smaller feature size, they actually switch to a 3D implementation that's called the 3D FinFET processor. And fin because this is looking like a fin, right? And so you have now the gate going around the fin and controlling the movement of the electrons. So in a 10 nanometer process, basically the minimum feature that you can build is this fin. And you can see this here in the picture from the 10 nanometer, Intel's 10 nanometer process. So these are two of these fins, and they have a distance of 34 nanometers, and each fin is about 10 nanometers wide. So why is this feature size important? We want to integrate more and more transistors on the chips, and you all heard about Moore's Law. So Moore's Law basically stated that we double the number of transistors on a given space every 2 years, and so we actually get a doubling of the performance every 18 months, right? And so this basically, the doubling comes from the fact that these process technologies get better and better. You can produce transistors with smaller and smaller size, and so you put more transistors on the same space. And because they are nearer together, also the clock frequency can go up, and so you get actually a bit more of speed up than just the number of transistors indicate. Yeah? So if we look a little bit at the history, we can see that this goes back in the table about the Intel processors till 2008, and it starts here with a 45 nanometer process, and then goes down every 2 years. Basically, we actually get switch to a new process technology and a new processor core architecture here. And so going down, we see that we had 10 nanometers here in 2019. The Cascade Lake processor was again 40 nanometer technology. Ice Lake is from 2020, also in 10 nanometers. And so now they switch to different names. So they don't call it 7 nanometer or 4 nanometer process because it actually, this term of the nanometers is actually used by other providers like Samsung, for example, in a different way. And so it was said for a long time that Intel is now not ahead of the crowd, but back in the crowd because they were stick with a 10 nanometer process, while Samsung and the Taiwanese producers actually went to 7 and 5 nanometers. So, and now they basically use a different naming scheme, which is sort of indicating that they are on the same level as the competitors. And so the current processors are the Alder Lake and then the Meteor Lake processor fabricated in the finer processes. So This indicates a little bit how much million transistors you can actually integrate on a square meter of silicon. And here are the processes. So we have the 10 nanometer here, so it's about 100 million transistors per square meter. And you see that for 7 nanometer, actually the density did not increase in the Intel process, but when switching to the 4 nanometers, they will double the density. And you see the density from the competitors here as well, the TSMC and Samsung here. And the IBM actually is at the 2 nanometer with about 333 million transistors per square millimeter. Good. So that is the basis for all our processors, and then what is done with these transistors, right? And I spoke about Moore's law, doubling the number of transistors every 2 years. There is a belief that Moore's law will end soon. So it did not yet end, interestingly enough. So they are still reducing the feature size, but the prediction says that the smaller the features get, the more side effects they will have. And so you cannot go through arbitrary small feature size. So you can see in this graph here that we have this increase in transistors due to the process technology as I discussed. This is over the years here, so it basically keeps increasing. You have more and more transistors on the CPU. But we have also seen an increase in the clock speed. So that was the second source of performance improvement, so that we went down to 18 months, doubling the performance, right? And the reason for that is actually that we need more and more power. The higher the frequency is, and power is a big issue. So you first have to provide the power to the chip, and then you have to get it out of the chip, so it's basically turned into heat, right? And so you have to efficiently cool the processor. Yeah, and due to that, they stopped actually increasing the frequency, and you can see that here in the green curve. Yeah, so you see that actually it flattened here in about 2010, right? So that is around 3-4 gigahertz. That is what you can currently find on the market for all the processors. Yeah. There is IBM, I think they actually have the power processor that goes up to 7 gigahertz, but all the processors, ARM, Intel, Apple and so on are basically stuck at this boundary since quite some time now. Right. So what to do then with the additional transistors that we have? Yeah. So actually, this is a trend that also started here in 2005. That actually we add more and more cores to the silicon. So cores in the sense these are little CPUs that are together on the silicon on the socket, yeah, and they can execute independently work. No? And so this number of cores is definitely growing, and we will see a few examples for that in a few minutes. So that is a way to still increase the number, the performance of the processors. What you see here, the purple curve here actually, or violet curve here, is a single thread performance. And you see that basically is stuck with the fixed clock frequency. Yeah? So the single thread performance does not improve anymore. So we actually have to parallelize our applications to get more performance, right? And so that can mean that you actually use really multiple cores, but it can also mean that you have multiple threads using the hardware more efficiently on a single core. Good. So the trends are basically we have multi-core processors everywhere. And so if I typically ask students that want to study here, or kids from school that want to study what they know, and we try to find out whether they have an idea what the processor, what the internals of a processor are, right? And the number of cores should be known to everybody, because that is an advertisement argument for the companies. When they want to sell you a laptop, typically you find this is a 4-core or 6-core processor, so you should sort of be aware of that if you are interested in computer science, I would say. Yeah? So, but it's surprising that this is not so frequently the case as I hope. Good. So that is the first trend, so multi-core processors. The second one is SIMD support, single instruction multiple data. That is that we process a set of data with the same instruction, and there is specialized hardware on these processors to do so, so-called vector units. So you have a vector of data, 2 vectors with 8 elements. You apply an addition operation, and all the elements are individually added up, and you get as a result also a vector with 8 results. Yeah? And that is definitely an important aspect for the CPU companies. They integrate higher and higher support for the SIMD operations, because data parallelism is everywhere. If you think about encoding videos or so, this is basically data parallelism. Yeah, you have lots of images, and each image you can split over cores, and then inside of a core you can work on vectors of the image. So that is an easy way to speed up applications, and so therefore they actually add this to the standard processors. So then we have caches. So all of you hopefully heard about caches, very important. So we have main memory in the systems, and several gigabytes, 16, 32 gigabytes of main memory, but this is pretty slow, right? And so to actually feed the processing power of the cores, we actually need faster memories, and so therefore in between of the cores and the memory we have caches, and these caches are static memory compared to the dynamic memory of the main memory. And so this is faster, and so by that you can keep data that you frequently work with near to the registers, and therefore the processor can more faster compute information. So then another trend is heterogeneity. So the processors actually not only have the same cores, but might have different cores together, because that is a general trend. If you want to get faster, you actually have to specialize, right? So you actually specialize your hardware for the computation that you have to do, and by that you get faster and probably with less energy consumption. So then we have typically hardware in the CPU to control the energy usage of the CPU. A big topic, energy, so data centers, they are the biggest users of energy in IT, and so to actually reduce the energy consumption directly turns into lower cost. No? And so it's important to optimize energy consumption, reduce it, and that can be done by adapting the processor dynamically to the needs of the application. So, for example, we can switch off parts of the processor that we don't need. If you have a processor and you run a single application with just one thread, and you have 8 cores, you don't need the 7 other cores, right? You can switch them off. You can, for example, adapt the frequency, the clock frequency of the processor. The lower the clock frequency, the less energy is taken. And if the processor is very fast but always waiting for memory, then you waste energy, right? So with a lower clock frequency, you would be as fast, but with less energy. Okay, so it's very important aspect, and all the companies provide hardware support to control the energy consumption. And obviously all the processors are now 64-bit architectures, so they have registers that are 64-bit wide. They can handle address spaces of 64-bit, and the processing units are also 64-bit wide. Good. So the challenge is, as I said already, feeding the processor. The memory hierarchy is important. Hierarchy, we call this because we have the registers that is very fast, and we have the first level cache, fast, second level cache, still fast, third level cache, slower, and then we have the main memory, very slow, and beyond that we have disks for virtual memory, for example, very, very slow, right? And so important is to use this memory hierarchy in an efficient way so that you keep the data as near to the processing units as possible. So here is a picture of a die, the Kaby Lake processor. That is a state-of-the-art processor, I would say, that you find in not the top fast systems, but in reasonably fast systems. So we see the areas of the CPU cores here. We can also see the so-called system agent, so that is managing the CPU. So for example, the energy control is located there. Yeah, and then we have here integrated on the chip also a ring interconnection network. So it basically is really a ring network, wires that go from one core to the other, and this enables the cores to communicate, right? So this is state of the art, I would say. Then we see the cache levels here. So on the CPU core you have the L1 and L2 caches, so they're very near to the computational units. And then there is typically a shared cache between the cores, so that is called the level 3 cache here. Yeah? And so you see that this is sort of distributed over the chip, so you have blocks that are near to the cores and other blocks that are further away. And you can imagine what happens if you program this. It's important to work on your local part of the cache, right? So if this CPU core should actually have the data probably in these cache blocks and not over here, because going to there they would have to go through the ring network to access this data. And so that shows already that even on a single chip you no longer have a uniform access. It really is important to think about where the data are located and to optimize for that. So, beyond that, we have here a GPU. Many of the processors nowadays comes with a GPU, so you don't need an external GPU. You want to have a display in your laptop, right? You need a GPU for that, but you don't need an external one. The processors basically have an integrated GPU and can use that. Good. So that's a Kaby Lake. The Skylake processor, and that is a server processor that is used in the SuperMOOC, for example, but these are classical servers combined into a parallel machine. So it's the Skylake XP socket here, and this has no longer a ring network, but it has a multi-dimensional mesh network on the chip. So that means that actually, we have many more cores here on the chip, 22 or so, I think, and they are basically connected by this two-dimensional mesh network. And if this core would have to communicate with that core, basically a message is put on the 2D mesh and then forwarded first in one dimension and then in the other dimension. That's called dimension order routing. So they always go into X and then into Y dimension. So to circumvent the problem of deadlocks on the network actually. So, and this gives obviously a higher communication bandwidth. You have more cores, you need more hardware to be able to communicate more information, right? And so that is the reason why we have these 2D meshes as on-chip networks nowadays. So, what is also in this Skylake and coming, probably we will see that also more frequently, is another level of non-uniform memory access. So we actually see that we have two memory controllers here. One is on that side, one is on that side here. And the chip supports what is called the sub-NUMA cluster mode. So you can basically make the cores that are near to one of the memory controllers work with the memory of that controller and not to go over to the memory of the other controller. You can in principle access all the memory, but there is an optimization that the data are placed into the nearby controller in these DRAM chips. So by that it becomes faster and it enables also a more efficient cache coherency protocol. So cache coherency means if you have caches in the processors and the processors work on the same addresses, then they have copies of the address and these have to be kept consistent, right? So if one processor writes the address, the other processor needs to be informed that there is a new value there, okay? So, and in such a network, it's implemented that you actually have a sort of directory. The directory tells the processor, oh, there is a copy, and this has to be updated, right? And so if the directory would be here, and this processor would access information that is currently up to date in this processor, this one would first have to go here, learn about, oh yeah, there is something up there, and then you have the communication. So that's not efficient, you can immediately see that. And by that, what we actually do is we basically put the directory information also near to that memory controller, and so we don't have these long distances for that as well. So another piece of information is this here. You might have heard about the thermal design power of the processors. That's basically the power that they can sustain, right? So they can use up to 205 watts and dissipate this power as heat again. So that's a maximum. You cannot go beyond that because then it might burn, and there is hardware obviously on the chips that make sure that this doesn't happen. But 205 watts is quite a bit, no? So think about they are powered with 5 volts, so these are 40 amperes or so. You even have to manage to get this power into the chip, right? So it's not just one pin, but you have many pins to actually provide the power to the processor. Good. Right. So important are the Can you
explain again why Skylake has better caching than the previous, what was it, the other one?
The question is why Skylake has better caching. So caching is actually an approach that is used in all the processors since a long time, right? And the caching is, I think, not really a very specific feature of the Skylake processor. So the standard is you have level 1, level 2, level 3. Level 3 is shared among the cores, and the other two are private. What is new is the directory scheme for cache coherence, but it's also was not developed here with this processor, but it's also something that is around since quite some time nowadays. Yeah? So here you see also the information about the caches, and this confirms what I said. Yeah, the caches are basically more or less standard, right? So you have level 1 caches, which are pretty small, 32 kilobytes here. Then you have level 2, still private in the core, 1 megabyte, and then you have a level 3, and that is 1.3 megabytes per core, so up to 30 megabytes of level 3 cache. Good. So you can also nicely see from here the latency. So the access to the level 1 cache is 4 cycles. To the level 2 cache it's already 14 cycles. then to the level 3 it's 50 to 70 cycles, and to DRAM, it can be hundreds of cycles, to get information from main memory. So that is basically the reason why you have to effectively use the memory hierarchy. So this is a Skylake core, and I show you the picture. I will not explain this here, right? That if you come to the computer architecture class, you learn about that. But what is important here is these units here. I talked about the SIMD units. You find them now on ARM processors, on Intel processors, AMD, all have them, right? This is to process data faster, and the current state of the art is that we have AVX 512. That's the instruction format for the SIMD units of Intel. AVX 512 indicates the number of bits that are processed in parallel. And if we talk about scientific computing, then we talk about double precision values. These are 8 bytes, and so we can do 8 flops, floating point operations per cycle in one of these units. And actually the processor has also 2 a bit older or not that powerful units. They support AVX2, that is only 256 bits, so 4 operations per cycle. And this in total, you can combine those to get 512, so you get 16 flops per cycle. And actually, if you combine, multiply, and add together, you get actually 32 floating point operations per cycle. And that is what gives the real compute power in these processors. Second, on the slide, you see the frequencies here. So there are different frequencies that are used for the processor. So the standard frequency is 2.7 gigahertz nominal. You can run it permanently at 3.1 gigahertz, but standard is 2.7 because it uses less energy. And then there is a peak, which is about 4 gigahertz. That is the so-called turbo frequency, and you can run for a short time, but not entirely, because then it has to dissipate too much heat. So these are basically the range where you can control the frequency. You can also go to slower frequencies, of course, but at LRZ, for example, for the processors, you get only up to 2.7 gigahertz, simply because they have to save energy, and only very few applications profit from a faster clock rate. In addition, there is this AVX units, the SIMD units. So if they are heavily used, they produce even more heat. And so if they are heavily used, the processor gets clocked down in hard rate to 2.3 gigahertz. Yeah. So then this is basically an example for server processor. Other server processors from IBM, the power processors, of course, but these are the 2 big competitors there. ARM is also now starting to get into the server market, but mainly they are in the mobile market, located with the processors, and the embedded systems market that I actually not talk about here. So ARM is basically originally a British company, and it was then bought 2016 by SoftBank in Japan, and recently acquired by NVIDIA. NVIDIA is a company that sells GPUs. The company itself develops processor designs. They don't implement processors. They basically develop the design and let it fabricate in Taiwan or so by companies that do that. So that is actually an approach that is now very frequently done. So Intel has own labs to fabricate chips, but many others like AMD or so, they basically outsource this and use these companies that do nothing else and producing the designs given to them. So these cores or processor designs are integrated in so-called systems on a chip. So they become part of a chip, but this is not the only part. There are other parts on the chip, like for example an encryption unit, right? And so therefore it's called system on a chip, and these are used typically in mobile devices. And ARM developed, there is.
Just little correction that ARM wasn't acquired by NVIDIA.
What?
Little correction that ARM wasn't acquired by NVIDIA.
What?
And because this deal failed.
This deal failed. Okay, good. So, also, we have to check this. He knows more than me, so he claims that actually this did not work out. So what is it then? It's still with SoftBank?
Yeah, it's still
Okay, good. So ARM basically, because targeting the mobile market, energy efficiency is even more important than in the server market, right? So it is that they developed this concept of big little. They combine on the SoC not only powerful processors but also less powerful processors. For many applications you don't need the fastest processors at all. And so by that they can save energy, right? And so here's an example. You have a cluster of A57 and A43. And so in the cluster switching approach, they can actually switch between the two clusters and use a green cluster here for times where there's not so much demand for compute power, or you can use a global strategy where you can actually distribute computation more flexibly among these big and little processors. So let's go to Apple. So maybe you are aware that Apple is also producing their own processors nowadays. So they basically use IP from ARM, but they actually extend the instruction set and also the internals, not like other companies that simply takes the IP of a core and put it on the SoC. No, they actually extend the instruction set and the microarchitecture. So, and for the iPhone and iPad Air, it's actually a bit difficult to keep updated always. So we have the Apple A14 here in the iPhone 12, for example. It's a 40-bit GPU, 64-bit GPU with 6 cores. You have 2 of these high-performance cores, 4 of the energy-efficient cores, and it has a so-called 4-core GPU. It also has on the chip other accelerators, which brings me to the topic of the accelerators. So we have a neural engine, we have a matrix multiplication machine learning accelerator, there are image and signal processors, and the production process is from TSMC, and it's a so-called 5 nanometer process, 11.8 billion transistors on the chip, and it's packaged, it's a combination with the memory in a package-on-package implementation, which looks like that here. So you can actually have one package, and on top of that package you basically have the connections. Here you put, for example, then the memory DIMM chips, right? And so you can actually stack them here together in a package so that you get higher density. So that is the Apple processor. A14, so more recently they introduced the M1, which is for laptops, and they actually switched from Intel processors to their own M1 processors recently, and there is now already a family of the M1, and you see the die shots here of the M1, which was released in 2020, and now there is also the M1 Pro and the M1 Max released in 2021, and these processors are now used in the Apple MacBook laptop, for example. You can buy it with the M1 Pro and the M1 Max processor. So the M1 core architecture, basically it's also based on ARM. It has 16 billion transistors. It's an 8-core CPU and an 8-core GPU. Yeah, the A14 was what was it, 2 cores or so, GPU, and the neural engine is also there. And for the CPU, you have 4 high-performance cores and 4 high-efficiency cores, because it's intended for more heavy workloads, so they increase the number of high-performance cores there. So we also have this big. LITTLE processing that I introduced for the developed by ARM. And on the chip here you can see that actually the 8-core GPU takes quite some space on the chip, right? This is the last level cache here. Then we have the high performance cores here, and these are the efficiency cores. There is a neural engine, and here are the interfaces to the memory, DDR4 memory. So if we look at the Pro and the Max, we see that the chips get larger. We saw that on the picture before. There are more transistors on the chips, and we are here in 57 billion transistors on the M1 Max. The CPU is the same in both of these chips, so 8 high performance cores and 2 high efficiency cores, so increasing the power with high performance cores. Then we have the GPU here with 16 cores, and on that side we have a 32 core GPU, so they double basically the capacity or the capability of the GPU. And that goes up to 10.4 teraflops. There's floating point operations per second. There is 32 gigabytes unified memory. Here we have 64 gigabytes unified memory. It's called unified memory because traditionally the GPUs had their own memory and the CPU had own memory. Right, and you had to send data from the CPU to the GPU, and then the GPU could visualize the data. So that is not really very efficient. So they now move to this unified memory. So it's the same memory that can be accessed from the GPU as well as from the CPU. And so data computed from the CPU will be directly available to the GPU. So that's is why they call it unified memory. And we see the bandwidth here also 200 gigabytes per second bandwidth for the M1 Pro, and it's doubled for the M1 Max. And the Skylake actually that is in SuperMOOC gives you about 250 or so gigabyte per second. So that's a bandwidth how fast you can actually send data from memory to the processor and the other way. Yes. It is for inferencing basically, right? So you can put neural networks there and do the inference into this neural engine. That's my understanding. So and the matrix acceleration engine is there to train networks, right? So that you can on the chip actually do the training. Good. Yeah.
So the M1 processor does not have any dedicated device memory, so it only has unified memory?
Yeah, so the memory is unified memory. No, that is for the CPU as well as for the GPU.
Yeah, but like when I access some of the older NVIDIA devices, they have unified memory and they have device memory also.
Right.
So this one doesn't have any of the...
So there's no device memory in that sense that the GPU would have own memory.
Okay.
No. So these are the die shots, and you can see that basically, this is copying the design from the 16-core GPU to a 32-core GPU. Yeah. So that is a picture. So you have the memories over here. This is the M1 Max in the middle, and then. By searching for what's going on, we see Apple also now has the M1 Ultra. It's not used in laptops, but It's basically two of these M1 MUX connected together, and that there is a so-called silicon interposer. So there are connections that were already visible when when the first screenshots, die shots came from the M1 MUX, which is located here, and here that these two M1 MUX can communicate. No? And so it's basically all the numbers are doubled that we had before. Yeah.
Just a quick exam question. To what extent do we have to remember these specs, like the exact numbers and stuff?
Okay, that's a good question. So the default answer, you have to know everything, right? So besides that default answer, what I really want you is to know about the trends. Yeah, what is state of the art? Yeah. So something like there is a change of the network, yeah, that you have multi-core processors, that there are ring networks or going towards multi-dimensional on-chip networks. This is important, the trend towards accelerators, and there are different examples that we talk about, yeah. So we have the SIMD units, we have the neural engine, we have matrix special tensor accelerators. We have them on chip, we have them off chip, right? So that's the next part, and so on. So I think that is what you should actually know. Yeah. So I cannot memorize how many cores are on the M Pro and M1 Max or so. Yeah. So I think that is not necessary. But one of the problems with the M1 processors is that the memory is basically connected directly on the substrate here with the core, with a CPU. And so you are no longer that flexible as in traditional systems, where the memory was basically in a memory bus and you could basically take out the DIMMs and put new DIMMs in there when there was a higher density DIMMs available, right? That is no longer possible. You buy the processor and the processor comes with whatever 32, 64 gigabytes of memory, and that's it. You can just throw it away afterwards. Good. Yeah, so now we go into the general purpose graphics processors. So acceleration is a point here, accelerated programming. And it's all about increasing the computational speed. So obviously for games, right? So you want to have more fancy visualization there. But obviously also you can use the speed for other processing. And that is what I will talk a little bit about here. So you can increase the computational speed, and you do that by reducing the energy consumption. To get the same performance, you need many, many more Intel processors, and that would take much more electrical energy. So going for a more specialized design, like what an accelerator would have, we can actually save energy. So, and that is both together is achieved by specialization. So basically you can have special operations that the processor or the accelerators implement. You can specialize in the on-chip communication, that you have a special communication that supports certain algorithms, for example. And you can also specialize in the memory accesses. So thinking about how much cache is needed, whether you need cache at all, and so on. This all could be specialized for the application requirements of the applications in that domain that you have this accelerator for. So there are three types of accelerators that I want to mention. These are the GPGPUs. Then we have accelerators inside of standard cores, the SIMD units. We talked about that already. And then we have FPGAs, field programmable gate arrays. That is also now really a trend to look into how these can be used in standard applications for speeding up certain parts of the computation. So we can also look at how they are integrated. So they can be nodes with attached accelerators. So you have the CPU, and then in addition on the board you have an accelerator. There have also been proposals just for an accelerator-only design, so that actually you have no standard core at all. Yeah, you have the accelerator, and part of that would basically take over the normal operating system tasks. And then there is also the model to actually have a booster, so that your machine would have a part of the machine would have these accelerators, and then programs that run on the machine can dynamically allocate a certain fraction of this booster for going faster if needed for certain computations of the application. So, first GPUs, general graphics processing units, used for visualization, and there are these famous libraries, OpenGL, DirectX, and so on, to actually program scenes and visualize it via a GPU. No? So NVIDIA basically started with looking into how these GPUs can be used for general purpose processing. And so therefore we call them now GPUs, General Purpose Graphics Processing Units. And this is using the GPU for other processing, not for graphics. And these GPUs are really very powerful if you have an application that matches what they offer. They combine everything that is state-of-the-art in computer architecture at the moment. So you have, for example, multi-threading, that you have a core which can run 2 threads at the same time, simply to make better use of the hardware of the core. They use MIMD, multiple instruction, multiple data. So these are different threads executing different instructions in parallel. SIMD I spoke about, this is data parallel execution, and they even also use instruction level parallelism, where actually instructions are not fetched and then executed, but you have a pipeline and you split the processing of the instructions into several stages there. Good. The challenges are, first of all, you have to program the GPGPU, and this is not standard programming. There's a special programming paradigm for the GPGPUs. You have to learn it and write your programs accordingly. So you cannot just take a program, compile and run. That's not possible. You have to rewrite it. Second, you have to coordinate the scheduling of computation on the system processor with the GPU. So the GPU is an accelerator. So you say, oh yeah, now I come to a subroutine called kernel, which I want to run on my GPU. So now you have to basically start it on the GPU, then you can do something else on your CPU, and finally you wait for the results from the GPU to be returned. So you can imagine that you have to learn how to do all that and how to make efficient use of these possibilities. So that makes programming more difficult. Then you have to manage the data transfer. It was mentioned that we have the GPUs have private memory, as they have graphics memory, which is extremely fast. And so in a typical system where you have a CPU and a separate GPU, you basically have to transfer the data first before you can process the data, right? And so you have to be careful when and how to do that. You have to update information and so on. So it complicates your life as a developer of programs quite significantly. So, and to support programming these accelerators, NVIDIA developed the CUDA language. And here is a picture, a schematic picture of such a GPU. It's a Pascal GPU. Basically what you can see, it's very regular compared to the die shots or so you have seen before, where you have here a bit and there a bit and something like that. Here everything is quite regular. So that is because it's optimized for data parallelism. You do the same thing on big sets of data. That's what a GPU does, right? And so there is a hierarchical structure, and there's one of these little blocks is called a streaming multiprocessor. So that is basically the base unit of processing. And then we have a bit of level 2 cache here. There's a private memory in each of these streaming multiprocessors. And then you have here, somewhere is access, here on that side, and that side is basically the interface to the DRAM chips. Yeah? So, looking at the streaming multiprocessor, it's again very regular design, right? So we see that we have, let's see, we have 32 floating point 64 CUDA cores. These are here's the DP units, right? Number precision units, these are the 64, and then we have 64 floating point 32 CUDA cores. So for single precision floating point values, these are these cores here. And basically you use this as vector processing. Yeah? So the logic here, the scheduler, which is somewhere over here, basically selects an instruction and it will be executed on all these 32 cores here in lockstep, right? So it's like a SIMD unit that I explained in standard processors. Now they also have specialized units, special functional units, load store units here and so on, so we don't need to understand this. But what I want you to memorize is that it's optimized for data parallel processing. Yeah? And it can do it very fast. So, then they use also a new memory, type of memory. It's called high bandwidth memory. So basically it means that we have a vertical stack of memory chips, and there are silicon vias through the chips, so that you get now in a clock cycle basically results from multiple chips. So you can really provide a high bandwidth. Yeah, you can provide the data with high bandwidth. And so these are provided because they actually have this extremely fast processing of the GPU, and so it's very important to be able to feed this processing capability here with data. So you see that this is also with a silicon interposer. It's done to combine these stacks here of DRAM chips with a printed board circuit, and finally also with the computational unit. So this is a picture of such a accelerated GPU accelerator. So you have the processing unit here in the middle, that's a GPU, and then you have the memories on both sides. This is the data from, I think one of the very last GPUs developed or started to be sold by NVIDIA. It's the A100. And so you can find here now all the information that we spoke about, right? 7 nanometers, TSMC is fabricating it. This is the size of the chip. It's quite a big chip. We have 54 billion transistors on the chip, so very comparable to the M1 Max from Apple. We can go down here, so you see here's the teraflops. So I don't know, but my estimate is that the number that I showed you for the M1 is also a single precision. So this is 19.5 teraflops. Before it was 10. So much more powerful. And what I want to go down here is so the bandwidth, memory bandwidth is 1.5 terabyte per second. Yeah? And the thermal design power is 400 watt, right? So it's double the Skylake processor. And the M1 Max has, I think it was on the slide 80 or so. Yeah, so right. So a nice feature, and that brings us back to cloud computing, is the MIG feature. multi-instance GPU. So in cloud computing, you know, these are servers, and you have a virtualization layer basically. Yeah? There's a physical server, and you get a virtual server when you ask for a server, right? And so there are multiple of these virtual machines running on the same physical server. What to do with a GPU that is attached to in the physical machine? Yeah, which of the virtual machines actually get it? And so with the multi-instance GPU feature, you can now in hardware partition the GPU. You can make it look like multiple GPUs. Here in the picture, it is split into seven instances. So these are by hardware separated 7 GPUs, small GPUs. Yeah, but it's only one physical chip, no? And so with that feature, you can actually, you partition, you slice the number of SMs, but you also slice the DRAM and the cache. So, and you can, the slicing is on a finer granularity, and you can determine how much DRAM goes to which of your GPU instances. Yeah, and by that you can control, now give a part of the GPU to a certain virtual machine, and it can be directly accessed from the virtual machine, and computation can be run there efficiently. And the other advantage is by having this physical separation, it gives you isolation of your data, and it gives you performance isolation. So the performance of one of these instances is not affected by the processing of the other instances. So very, very novel step in bringing accelerators also to cloud servers. So then we have the field programmable gate arrays. So they are also used nowadays as accelerators. And maybe you know a little bit about field programming and gate arrays. Basically, you can program algorithms in the hardware. So we have the style microprocessors, we have these FPGAs, and then we have ASICs. Yeah, so these are, you make a specialized chip for what you want to process, right? So these are the alternatives, let's say. And so an FPGA gives you the opportunity to improve your code, the processing, energy-wise and performance-wise, on hardware level. Yeah, you can design a very special hardware for this algorithm that you want to execute. So basically, is an array of logic gates, and you determine how they work together to implement the function that you want to execute. You can program it, you can reprogram it, you can remove a program from it. Yeah, so that makes it quite flexible. Besides these logic gates, you also have specialized functional units there, like a DSP, a digital signal processor, or memory blocks that are located in between of these logic gates. And we also might have, I think it's written down here, yeah, so I come to that. So we have static memory, that is called block memory. It's basically here in between, and you can access it from your logic blocks here. The clock rates are not really impressive compared to the standard processors that I showed you, which run on the gigahertz. This is much slower, but you actually do only what you really need to do, and by that these FPGAs are very efficient. So programming is done in VHDL typically. There are also higher level interfaces, but finally you have to understand how it's basically mapped into the hardware description there, and so it's fair to say that you have to really learn a hardware near programming language for developing codes that you can then sort of burn into the hardware. So there are two big players, Altera and Xilinx. Altera was purchased by Intel, and the cost for the FPGAs is decreasing while the costs for ASICs is are increasing because the more denser process implementation, right? This requires more careful work, other materials and so on, and so that makes the cost for developing an application-specific integrated circuit much higher. So typically what you can do is you can actually get synthesized CPU cores, so these are soft cores, and you could basically put them here into these logic elements, but this is typically the performance is slow. So what many of these chips now have are hard cores, shown here as CPU. They are then connected to the array of logical gates for the special purpose execution. So the area where the FPGAs are actually used is this space here. We have different processors here, only numbers of processors, right? So we don't see which ones are there, and we have in the y-axis here the energy efficiency, million operations per milliwatt. And we can see that with the microprocessors, we are on the lower end of the energy efficiency. Then we have here DSP, digital signal processors, still very specialized processors for encoding videos, audio. Yeah, there you use these DSPs. And then we have here the ASICs, special purpose hardware. And so special purpose hardware can reach to a very high energy efficiency, but it comes with the problem that it's a long process to implement it and an expensive implementation. So, and in between we have the FPGAs here. So you basically get to quite a good energy efficiency for whatever you want to do there. Because you actually work on hardware level, but you can program it. It's still flexible, right? And by that, you can combine both. And that is the reason why FPGAs are now really en vogue and very interesting for many applications. This is only to motivate what you can do with an FPGA. So a big data scenario, you have lots of data in your database, maybe it's an in-memory database, and you want to search for information or combine tables or whatever, right? So usually it works like that, the CPU does it, right? It fetches the information, detects whether it's relevant for the query, would deliver it, the rest was fetched for nothing, right? And the memory bandwidth to the DRAM memory is actually critical, and so this will not be very fast, right? And so what you can do, you can actually in between put an FPGA here. So here is the main memory, here is the processor, and things like searching for relevant records can be done on the FPGA. So the FPGA has a much wider access to the DRAM. Can pre-process this, you can burn this algorithm into the hardware of the FPGA, and by that you can already select the important records and only provide those to the processor. Yeah, but obviously you can also use this, for example, in networks. There's a network interface card. On the network interface card, we could have an FPGA. You want to actually do direct processing on the data that arrive on the network interface card. So you program the FPGA to do exactly the algorithm you want, so you don't have to even bring the data to the CPU, makes the CPU do the computation. No, you have your FPGA on the network interface card for that. That is another example for speeding up computation with the help of FPGAs. There's also lots of research to use FPGAs for accelerating neural networks and so on. So this is really quite an active research area. Okay, so Intel and Altera together deliver the Stratix 10 chips. That is probably not the most recent one. It has the so-called HyperFlex architecture, and they provide it to cloud computing and data centers. So like accelerators connected to the physical servers, you also have servers now with FPGAs, and you can allocate those dynamically in the cloud and use them for processing. So, right, so let me just show you here the picture of the Intel HyperFlex architecture. So you have these adaptive logic modules. Basically what these are lookup tables. Yeah, so you have the inputs and you have a lookup table which creates the appropriate output of the function that you want to compute, right? And so you have quite a number of those. You also have these DSPs and so on in this architecture. What is important is that at all these cross points of the connection network, yeah, so these modules obviously have to be connected, and you program which output from this module goes to which input of another module. And so all these connections, and also the here in front and at the end of the ALM, you have registers, and you can use this in a pipeline mode. So you can actually pump data from the left side to the right side, for example, through this hardware matrix, and then in lockstep basically the data flow to the next ALM to be processed there. So pipelining, is also a very important concept, general concept to speed up. In addition to parallelism, where you run different operations in parallel. In pipeline, you basically split up an operation into steps, and then you can overlap the execution of different steps of different instructions. And that is the same you can do on the FPGA here as well. Good. This is an example for an accelerator card. You basically plug it into PCI Express bus, and here is a chip with surrounding infrastructure. And here is actually this QSFP28 are basically connectors for fiber optics cable, and you can use this card, for example, to accelerate in-network processing. Then we have shared memory systems. I think I have only one slide for that. So it's basically that you combine multiple of the processors together, and these processors can access the same memory. And so if the processors do computation, they can exchange information by writing into the memory and reading from the memory. So we have a single physical address space here, and you simply do load store operations to the address space and you access this memory. Very important is a non-uniform memory access, so it's important which physical memory you actually access. We saw that in the M1, for example, you have also multiple memories, and some are nearer, some are further away, and so you can optimize your code by taking care of that. So here is an example. This is a SuperMOOC node. We have this is not a SuperMOOC NG. It's a SuperMOOC older SuperMOOC system. These were Sandy Bridge processors, but in principle this is showing you clearly this NUMA architecture. One processor, 16 gigabytes of memory. The other processor, 16 gigabytes of memory. All the processors can access all the memory. There is a connection here between the processors, but it's slower. So for example, the local access is 50 nanoseconds here. If this processor would go there, it's 90 nanoseconds. So it takes almost double the time to get information from the other ones. Therefore, it's called NUMA, non-uniform memory access, so the access time is different. No? So you program this with a wide spectrum of programming interfaces. We have threads typically to run in parallel. There is automatic parallelization. There is OpenMP. There are lots of things, and it's a well-established technique, I would say. Yeah, it's not easy to handle because you have to synchronize what's going on in parallel. but due to this shared memory, it's quite easy to do. And data locality, yeah, you basically have to think about where you put the computation and where the data is located. So we have this NUMA character of these machines. And so you really have to optimize for that, and you put a thread near to the memory in which you find the data. No? So that is called affinity, and the thread has an affinity to certain data, and hopefully you place it at the right processor so that it's then near and can fast access the data. The alternative to shared memory is distributed memory. Distributed memory means we have individual nodes, processor plus memory, we couple them together with a network, Ethernet, InfiniBand, whatever you can think of, and we let them compute together and they exchange information by sending messages through the network. Now that's the difference. And to program this is even a bit more difficult, or it's definitely more difficult than shared memory programming. So there is a standard called MPI that is widely used in parallel programming in HPC, and that is basically allowing you to send messages from one process to another process. Yeah? So that's this point-to-point communication, but there are also collective operations so that you want them all to do a certain communication pattern. Good. Yeah, so these are also called clusters, these distributed memory architectures. So it's looking like one machine with a number of nodes. And that is also how cloud data centers are set up. Yeah? So you have clusters of servers. In the servers, you have then these NUMA nodes that I introduced. And so this is the basis for your virtual machines that you actually run there. So a few more words, yeah, a bit more time for data center, because that is in the heart of cloud computing. So how do they look internally? This is basically from LRZ, right? So, but the data centers are all set up very similar. So you have the racks here, and the racks are basically on what is called a false floor. So there is another floor below that where all the cabling is done, right? And this is actually 180 meters high, so people can walk the second floor here, and for example, putting the cables and so on for maintenance. So the other thing that is important in data centers is how to power these processors. Yeah, so there are, NRZ has something like a few megawatt of power going into, right? So this is basically the connection to the power company here. And from here, we basically provide the power to power distribution units, and from there it goes to the racks, and the computation is done. So one important thing is uninterruptible power. Yeah, LRZ should not immediately go down if there is an outage. So we need uninterruptible power, and there are two things that are typically done in these data centers. You have batteries, and if you go to LRZ and someone would take you in the cellar, you could actually see rooms full of batteries that you have in cars, right? So these Blei Akkus, no? And so these batteries are then used for the very beginning of the power outage to actually provide power to the machines. And while this is happening, there is a diesel engine, and it's like a big ship engine, right? And that is connected to a power generator and would produce a power afterwards. So the diesel engine, it looks really like that in LRZ. They are in hot standby. They are actually hot, so that they can be started fast. They need a bit of time to synchronize with the frequency in the network, and so after a few minutes they can actually then provide the power for for the data center. So yeah, this is very common in all the data centers. On that side here we have the backside of a data center, that's the cooling. Right, so all the electrical energy is converted to heat, and so that has to go somewhere, and that means we have to cool, right? And so at the very end, the heat goes out typically into the air. There might also be a possibility to use the heat for other purposes. So a swimming pool, for example, to heat a swimming pool or to heat offices in winter time, that's what LRZ does. So, how do we get the heat from the racks out of the building? Okay, so typically there are multiple of these circuits here. So we have a heat exchanger here, which basically sucks in the hot air and then cools the air down, and the air flows back into the compute room. And so this heat exchanger is actually coupled through a water flow. So we get in cold water here at 7 degree cold water, and it comes back at 13 degree cold water. And then there is a chiller, and we take out the energy produce a 7 degree cold water in the chiller with the help of additional electrical power, and then we get water of 35 degrees, which can be cooled on the rooftop with cooling towers. And then this water flows down with 29 degrees again, goes into the chiller, and that's the way how to cool. So you put additional energy into the cooling of your data center. So LRZ actually uses two things that are interesting here to see. First of all, we have this chiller stuff over here in the picture. Then we have down here standard racks. They are cooled in quite some years. A few years back, actually, all the servers were cooled by air. So fans, and you basically cool with air. So this is now changing. We go back to water cooling. There are two concepts here. The first one is the back door, rear door cooling. So you have one door, which is basically then cooling down the air used in the server with the help of a water Kreislauf circuit, right? So basically we see that here. So we get here cold water of 23 degrees going into the doors, and then out of the doors we get hotter water. It goes through a heat exchanger to cooling towers. No? And here is SuperMOOC. There it's actually different. So we have hot water cooling in SuperMOOC. So actually we have water with 45 degrees going into the racks, and we get 55 degrees out. It's not this concept of rear door cooling. What they do is they actually have, this is one blade in the server, and so basically this is a cold water inlet, and then there are pipes that go to the important or very hot parts. So the memory is there, these are the CPUs. There is also some networking here that is cooled, and then the hot water basically goes out here. And that is significantly hotter than before. That has a disadvantage. The CPUs actually need more energy if the temperature is higher. That is a disadvantage, but the advantage is that you can easily cool that on the rooftop. You don't even have to have wet cooling towers, so this normal cooling over air works there. So very little energy going into the cooling here in this machine. And so there is a very important metric to compare data centers. It's a PUE. It's a power utilization usage effectiveness. And that is used to compare the data centers. And the lower, the nearer this value is to 1, the better, right? So what is it, the PUE? It's the total facility power, so all the energy going into the data center divided by the IT equipment power. So that is the power that is used by the racks for computation. Yeah, and you have additional power energy going in there for your offices, but more important is for the cooling, right? And so the PUE is always higher than 1, right? So to reach 1 is actually the goal, so that you actually don't have additional power going into the data center. All the power is really used for computation. And there is also this ERE, the energy reuse effectiveness. So that is if you actually reuse some of the energy in the heat of the servers for other purposes, then this is basically subtracted from the total facility power because you use it for other purposes. And there are 2 ways to do that. I mentioned that you can heat offices or a swimming pool or so. And the other way is that you can actually turn it into electrical energy again and use this for either cooling or for running your machines. Yeah. So, and to get the PUE down, one of the ways is actually to place data centers at places where you have free air cooling easy free air cooling, so like Iceland or so where it's cold. So put a data center there and you can immediately reduce the PUE of your data center. Good. Besides looking into how to efficiently use, that is basically showing this warm water cooling. You can save up to 35% of the energy with a lot of different techniques that you combine for the new machine that was calculated by LRZ for the SuperMOOC NG. So we want to switch to green energy, so that means that we first go for energy efficiency. Yeah, we want to use as little energy for the computation as possible. So it means we look at the PUE, we might use something like energy-aware job scheduling, that you actually place a job on servers that are best suited for the computation. Or you can look at the DVFS, the dynamic voltage and frequency scaling, and you can select the frequency of the processor to reduce energy consumption, maybe without even reducing the performance for a given application. And besides making systems more energy efficient, you want maybe also to reduce the carbon footprint of these machines. So you want to power it from green energy, not from brown energy, right? And we all know that green energy is not constantly available. So that means we need actually methods to migrate computation between data centers at different regions in the world, right? So for example, we could migrate to Sweden from Germany if there is more wind and the wind turbines are producing more energy than actually can be used at the moment. So by dynamically moving computation there to reduce the carbon footprint, that is something that also people are currently really after. Good, and I think that's the last slide. This is only the summary slide. We could have a short break now, and then we introduce the first exercise to you. If you want to get out, maybe like 2 or 3 minutes, stretch your, wake up again, that would be great.
I just opened Moodle and I've seen that we are supposed to register for the groups. So I have not registered for a group because I have just seen it today.
The group one?
Yes.
Just send me an email.
It's recording, so
I would have a question regarding the course because I don't have officially assigned a place in online, and I wrote an email and you added me on Moodle and I have a group so I can conduct this exercises. But then would I be able to do an exam or do I need to wait for an
For
official?
the exam, usually there is a separate registration.
Okay, so there are like no connection that if I don't officially have a place into
It's
online.
kind of like a hack.
Okay. So if I'm on Moodle and I will perform all the exercises, then I can easily take it.
Yeah.
Thank you.
Also ich bin relativ sehr frei, was das Thema anbelangt. Genau, im Internet ist halt immer die Frage, wie verlässlich dann die Sachen sind, die Datensätze. Also vielleicht haben Sie nicht was Ihnen direkt einfällt, das ist auch nicht schlimm. Vielleicht fragen wir mal.
Also jetzt so auf Anhieb nicht, ja. Mit den Studenten und so, aber das ist jetzt nicht so gut. Aber wenn Sie mir mal Ihre E-Mail-Adresse geben, dann würde ich mal rumhorchen. Vielleicht jemand, der uns da weiterhelfen könnte.
I forgot to register. I did not know that I have to register.
Yeah, just send me an email or put it on the private post on the Piazza. Or put it on, send me an email actually.
It's on your. Can I just participate in this exercise?
Yeah. Send me an email. Do you have any group already planned with someone?
Sein kann
Okay,
irgendwie
group.
aus
Okay.
IoT soll dann eine Seminararbeit schreiben, heißt Projektteil und dann irgendwas dazu analysieren, sowas die also zum Beispiel dann irgendwie Industrie IoT optimieren oder so oder rausfinden kann, wie viel Energie wird da verbraucht oder also wirklich komplett beim Thema
Und ein Use Case oder sowas. Also wir würden praktisch IoT einführen, was das ist und so weiter und dann ein Beispiel dazu
genau.
präsentieren. Ne?
Wobei also ich bin auf ganz, also wie gesagt, ich bin bei dem Thema komplett frei, es muss halt schon IoT sein, aber ich brauche halt irgendwie einen Datensatz. Ich habe jetzt im Internet schon so ein bisschen was gefunden, zum Beispiel, wo dann irgendwie da ging es um so Wärmepumpen oder so, wo dann die Ausfallquoten irgendwie, dass die dann vermeldet wurden, dass man eben da sagen kann, man würde das irgendwie dann optimieren oder vergleichen mit, wenn man diese Analyse nicht hätte.
Das ist sehr spannend, diese Digital Twin, wo man praktisch Daten aus der realen Welt dann in so einem virtuellen transportiert und da dann sowas natürlich schön. Da haben wir am Lehrstuhl auch wir haben eine Gruppe, die mit einer Firma zusammenarbeitet, die Turbinen oder sowas herstellt und die verwenden Akustik, um Fehlerzustände zu erkennen. Ja, sowas wäre vielleicht, da könnte man sicher was machen. Ja. Ich werde die mal ansprechen. Schicken Sie mir mal eine
Ich
E-Mail.
schicke gleich eine Mail und
Dann gucken wir mal, was wir
also wenn Sie nichts finden, ist auch nicht schlimm.
Ich denke, Sie brauchen eigentlich nur irgendwie ein Beispiel, da muss ich mir was zeigen. Sie brauchen gar nicht keine Daten, oder?
Doch, also das muss schon, ich brauche irgendwelche Daten, die ich dann...
Die analysieren Sie das oder was?
Genau. Also Alternative wäre halt einen Fragebogen entwickeln oder Interviews durchführen, aber ich bin halt gerne auf der Datenanalyse-Seite.
Gut, also machen wir mal so, ja?
Ja, vielen Dank.
Okay. Gut, then
So I can start.
you start.
I think this is better actually.
Yeah, that is quite good.
Yeah, so because otherwise I have to slide with this one, so it's tricky.
Yeah, and
But
you
with-
can even point. I mean, this
Yeah,
pointer is
with
not
this much better.
extremely strong, but I think it will.
Yeah, it's fine actually. Hi everyone. So let's start with the exercise. So today the exercise is about the application development using Node.js. So as I remember last week, many of you already know Node.js. So I will not go much into the details of Node.js, a bit high level overview and what the exercise is about, what the code contains and all that stuff. So before going into the detail of the exercise, two things. So first, the deadline for the group selection is over. So I hope every one of you already have a group. And the second, that I posted on the Moodle the Google Cloud link for getting the credits for the Google Cloud. So you can get that credits and you can use it for this exercise. So let's go into the details of what Node.js is, or introduction to Node.js. So before starting Node.js, so as you might have already know about kind of like a 3-tier application or a web application, which consists of usually a user like you, and you are using either a web app or a mobile app for opening that particular application, which is interacting with a backend, and this backend could be written in any language. We will write that backend in Node.js, and this backend is connected to a database for fetching some data like a user's data or some other kind of a data. And this whole together forms a kind of like a small 3-tier application. Why it is called a 3-tier? Because it has a front end, which is a web app or a mobile app, and a back end, and then the database for fetching the data. So then the next question comes is, when you open a web application on a browser, so you usually have to do some certain kind of a rendering. So with that particular code which is getting rendered is a JavaScript code. And how does this rendering is done? So you have a browser, and this browser usually have a JavaScript engine. And this JavaScript engine takes the JavaScript code, and this JavaScript code is for the web application which you are opening. And this JavaScript engine converts that particular JavaScript code of the web application into the machine code which runs on your laptop or your computer, and that's where you see the web application rendered on the browser. So there are different JavaScript engines in different browsers. So one of the example is the Microsoft Edge, which has a chakra. So how many of you use Microsoft Edge? I think very few are very rare. So this JavaScript engine is very slow, so that's why people usually don't use the Microsoft Edge over here. The next one is the Firefox, which has the spider monkey. How many of you use Firefox? So mostly maybe Linux ones or prefer the Firefox one. And then the last, which is the Chrome, which is based on the V8 engine. So I think many of you must be using the Chrome browser. Any other browser which anyone uses? Yeah?
I'm using Brave.
Which one?
Brave.
I'm not. Do you know which JavaScript engine they use?
This is V8.
It's a V8. Okay. And there is the one missing over here is the Safari from the Apple. So does anyone know which JavaScript engine they use? Yeah?
WebKit?
Yes, it's based on the WebKit. It's called as the JavaScript core. Yeah, so there are different JavaScript engines for different browser, and that's why if you open a web application or a website in different browser, it is shown differently sometimes because they have their own code for converting this code of the application into the machine code. So the next question is, how does the Node.js comes into the picture now? So as you have seen, there is a JavaScript which only runs in the front end, and there is a back end which is certain kind of a different language. So as you see browser this, until 2009 there was the only way for running the JavaScript code in the browser itself only. But in 2009 this guy named as Ryan Dahl, inventor of Node.js, what he did was he took the V8 engine from the core and wrapped it around a C++ program. And this C++ program is called as the Node.exe. This is where the Node.js got originated. So now you can run a particular code within this C++ program and use it for the server as a backend also. So the advantage of this now with the this particular embedded of a V8 inside a C++ program is now you can have the JavaScript both in the front end and also in the back end. Yeah, so this line that the JS was added in for just naming of the product. So additionally, so as if you already have using the Node.js, so there is within the Node.js, it's an non-blocking asynchronous nature. So this means that a single thread is handling the multiple requests. So like everything is done by a single thread only. So it's a single threaded program which is written by the node.exe. So if you are requesting, let's say, a database or doing a certain kind of a computation, then what this node program does is, so it will put that program into a call stack and move it to the next request to handle it. So that's where this call stack is called as the event loop. We'll come over here. So you have a single thread, and this single thread is over there is an event loop which is monitoring the event queue, so for various events in the stack. And now if you do a request to this single threaded application, and multiple requests goes through this event loop over here. So in the next slide we'll see more detail about it. So this event loop, what it does is simply iterate over this event queue, which is basically a list of events and callbacks of completed operations. So now you have multiple requests, goes through a event loop, which is a single threaded, and now that request suppose wants to do a database handling or want to get a number of users from the database. So it will do a register a callback, so this event loop, and this would be an intensive operation like a file system, database access, or certain computation. And once it does the callbacks, it will move to the next request to handle the next request. And once this particular request, which is doing a intensive operation, is finished, it will come back to the event loop by like a callback mechanism. And once this callback is finished, then the response is sent back to the user that my callback is done now. So now does anyone see what could be a problem with this event loop? So maybe I can tell. So like if you are doing, if you have seen in the browser, sometimes if that browser and application is doing a certain computation task and it is stuck over here that it doesn't register a callback, and so it's only in the saying single thread is handling that particular rendering of that application, then you cannot do any other task. So that's why sometimes in the browser if you see like unresponsive error, so this error comes from this part over here. So that's because it's a single threaded application. So now some small things about Node.js. So as you know that it's a platform built on Chrome's V8 engine, and there's a core is in the C++ and the backend is the V8 engine. The best part is that it can handle thousands of concurrent connections because it's a minimal overhead on a single process. So one thing which everyone confuses that it's not a web framework or it's not a programming language. It's kind of like a runtime environment for a JavaScript code. So it works, as I explained before, that it works on a single thread using a non-blocking IO calls. So now the next question comes is when not to use the Node.js. So when to use first? So like if you are doing a certain kind of a real-time applications that has a high volume of short messages, so because it's quite fast, it can handle those short messages over there. Other use case is the fast and the scalable environment. So like its ability to process multiple requests at a lower response time. So that's where you will prefer to use the Node.js. So one example could be like a single page web application, SPS, which are usually called as. Can anyone tell when not to use Node.js? Just one line, one word. Yeah? Yeah. So he's right. So when there is a CPU heavy jobs or a resource intensive job, so you should not use the Node.js because then you are stuck in that event loop which we saw earlier, and you will not be able to do any other task within the event loop. Yeah, so lastly, a point that you should also not prefer to use it on the simple web applications like which you are doing nothing, just displaying a front end and like I said, front-end display, nothing in the back end. So it's better to use other languages like PHP over there. Node.js is not meant for them. So one example where how this Node.js helped to increase the efficiency or the performance. So this is a this is a PayPal case study. So what they do, so I hope everyone knows PayPal. Does anyone doesn't know about PayPal? Yeah, that's a good thing. So the first line you can ignore. So it's a kind of like an online payment system, which they were using the Java in the backend for processing the user requests. So this had them a lot of problem, and then they migrated their backend to the Node.js. So what happened that they found that it was built twice as faster as with a fewer people, written in a 33% fewer lines of code, constructed with a 40% fewer files, and it's double the number of requests per second it could handle, because the Java is, as you know, it has its own JVM in the backend, so which is quite heavy. So they could, with the Node.js, they could handle double the number of requests per second. And lastly, the 35% decrease in the average response time for the same page with Node.js. So this is just one example. There are many other examples where people use Node.js, and now there are even for more better languages than Node.js like TypeScript or Go, which people prefer. So another module within the Node.js is the Node Package Manager. So this is for installing and like adding the programs within the Node.js. So like if you want to install a package, this is where this Node Package Manager helps. So it's easy to specify and link the module, so that if you want for like from your laptop to another laptop, so it's easy to put those packages names, and then you can install it on the other laptop as well. So and these get installed inside the node_modules folder. So if you do like a npm install express, so express is for creating a kind of a small web server, it's a web server application. So if you run npm install express, it will be installed inside the node_modules folder. And there is a annotation or a parameter to that which specifies --safe. Then this framework or the module which you want to install would be put inside the package.json file within this whole application. So we'll see what this package.json file is. And if you specify -g, then it's globally installed for your whole computer itself. Some of the popular modules are Express, which is for web development framework. Then the Connect for HTTP server kind of a framework if you want to build it. Socket.io for server-side WebSocket based applications. And lastly, Mongo and Mongoose. So this is for connecting to the Mongo database. So we will be using Express and Mongoose for building our application as part of this exercise. So as I mentioned earlier, it has a package.json file. So it's always present inside any application which you are building in Node.js. And it tells how the package or the application should be structured and what all dependencies are to be part of the Node.js application. So on top, you can specify the name of the application, then the script. So like if I run npm start, so this script would be called, which is a node, and then the main file of your, so like if you run a C++ program, then there's a main program. So over here it would be node client server.js. So the client server.js would be the main file of your application. Then you can specify the dependencies, like which dependencies are to be required as part of this application, like over here the Express. And if you do --safe, then it will be put over here as part of this dependencies along with the version number. So this is a bit about the Node.js and the package.json file. So another important part of this whole building the web application is the REST APIs. So does who all uses the REST APIs? I think you must be using all of them, because if you open any website or something, so they are using the REST APIs for getting the data. So the REST stands for representational state transfer, and it's based on the resources, like it's whatever the resource is in the backend, like a user information or some other resources. So that's which it gets from there. and it's typically transferred between the clients, so like your browser to the server within a certain action. So like typically a JSON or an XML transfer would happen there. And there are 6 constraints which needs to be part of any REST API. When you are writing a REST API, it should fulfill these 6 constraints. So one of them is the uniform interface, that it should have this HTTP, which we call it as the CRUD, get, post, delete, and the put part method into it. The second one is it should be stateless. So by stateless, I mean that the server should not contain any client state. So no session, no history should be maintained by the server. So every time the request comes, it's like a new request for the server. So that's where it should be stateless. And it should be built on the client-server architecture. So like you have a client on the web browser and the server in the backend for handling it. The fourth point, the request or the data should be cacheable. So like whenever you are transferring the client to the server, so in between you should have a interface for caching the data of the client or the server, whichever the client is requesting. And the layered system, so by layered system it means that a certain APIs can be on server A, certain APIs can be on server B. So it's usually not like it's not mandatory to have this, so it can be like one can implement everything together on a single server also. So, but it's recommended to have a layered system architecture when building a REST API. And lastly, the code on demand. So this is very optional. So if you want to send the code from the back end to the front end, so that can be implemented also through the REST API. So over here, so I think in the application which you will be building, we will be sending a backend code from the backend side to the front end. So we'll see an example of this, how this code on demand is being used also. So one example of REST API, so over here you can see a certain URL, which is can be an API gateway URL or a load balancer URL, like a common website. Then there is a context, then the version name, then the resource, like I want to query the resource of the users, and then lastly the queries. So which user I want the information for, like with the ID 423. And this context and the version and the resource together form the URI, uniform resource, I think. Yeah, uniform resource identifier. And then you can get the JSON file over here, like ID, name, and the status. So this is a bit about the REST API. So does anyone know what nowadays also people prefer to use instead of the REST APIs? So there is a newer, yeah. So nowadays there are applications or the website which uses the GraphQL. So like Twitter or Expedia or Shopify prefer the GraphQL based queries because they are much faster and they overcome the limitations of the REST APIs. I will not go into the details of those things. So then the next part which we will be using as part of the application is the MongoDB. So anyone have used MongoDB over here? Just used for building an application or something else? Anyone? Okay, so it's some course actually, okay. So MongoDB is an open source document database which is based on the NoSQL. So because it's NoSQL, it doesn't have any schema. So it can store all the JSON data into the database. And this JSON data is represented by a document. So it's in the MongoDB terms, it's called as a document. And so like over here in example, ID, name, and the status. So this is a JSON file, JSON not file, I would say it's a JSON document. And this is called as a document within the MongoDB. And within a MongoDB, a collection. So it's a collection of many documents, like many JSON objects. And the group of the collection is called as the database, so which holds this group of collections. And so if you want more information, you can check over here. So we'll not go much into the detail how it is built, how sharding is done. So just a high-level view of what MongoDB is. So now the next part is the installation. So how one can install the node and the npm. So I'll give over here only the information of how you can install on the Linux Ubuntu over here, but there are online links where you can find how you can install on like Apple or Windows also for building the application. So usually there is a link, you go over there, get the source, or you can also install through a package, Node.js package, apt-get install Node.js. And similarly for the npm also you can install apt-get install npm. And once it is installed, then you can run the node -v, which will give you the version number of the node, and npm -v, which will give you the version number of the npm. And for installation of Mongo database, so there is a lot of steps. So that's why I didn't put it over here, and because these are getting updated from time to time with the newer version of the Mongo database. So you can check over here on the link to get how you can install the Mongo database on your laptop or your virtual machine. So now let's go a bit detail into what the exercise code is. So the data directory structure of the application which I have provided you consists of few things. So over here you can see slint and editor config. This is usually to set how much indentation within when you are putting it from one laptop to another laptop, so that the indentation remains the same and should follow a certain pattern like double quotation or single quotation, so that you can specify within these files. Then the package.json file, which we checked for creating the dependencies. Then the server.js, which is the main file within the application for handling, for creating the whole application. Then there are models. So models is for interacting or putting the data like the schema. So over here an application which has a model of the books. So we will be using an application which has a book schema. So like the author name, the book name, all that information will be part of these models. And then there are some public folder which represents the HTML front end side of the web application. So we will not go into this detail because it's just the front end, like the CSS, normal CSS, and the HTML. So similarly the views part. So now let's see what this models contains, the books.js. So we are using Mongoose to connect to the Mongo database. So as I mentioned earlier, so you can check over here to get more details on which queries it supports and all that information. So first thing you do is import, or like in Python or other language you import it. So here is like a require, so you require this Mongoose. And once you have the Mongoose, then you can define the schema of what kind of data you want to store in the backend. So this has like a title, author, release date, genre, rating, etc. And then you can export it back. So like over here, I'm exporting it under books model from this file, so that anyone else who wants to use this model can use it with this name. And within this folder, there is an index.js file which you can specify to contain or connect to the Mongo database, and also which model schemas you are using. So currently we are only using the books, but if you have more schemas, so it's better to have this index file so that you can list all the schemas and import them over here. And then comes the main part, the server.js, which is the main backend service file, doing all the things. So as part of this, we are using the Express for building the web server. And within the Express, there are certain requirements like this URL encoded and the express.json. So this is for getting the entire body portion. So like if you fill a form within the UI, it goes into the backend as a JSON and stuff like that. So that's where you have to do this. That encoding is done through this JSON or a URL based encoding. And then you specify where are my static information like the CSS and the front end files. So this goes over here. So now the main part, which is the REST APIs, which are part of this application. One of the REST API, which is the GET. So this is the root endpoint, which gives you the index.html file, the front end of the application. So here you can see we are sending the code of index.html file to the front end side. And the parameters for this function are the request and the response. So request comes from the user, response which I send back to the user. The other API endpoint is the /API, which is just, we'll see what is this /API is. It's giving the information of what all APIs are part of your application. So as part of this slide, I want to mention about, so this point over here. So this and this part are quite similar. So if you see, these both are quite same. So you can either represent like this or the above way. So it's an implicit declaration of the function within Node.js. So now, so the first part, which is the /API/books get request. So what does this API do? It gets all the books information stored in the Mongo database and send it back to the user. So it's over here, you can see, so like over here, it's searching for the db.books. So it finds all the books information. So I don't specify any parameter within this brackets, if you can see. So if you specify any query, you can specify over here, like which book or the URL or the name or something over here. So and then it finds all the books and return as a JSON to the front end, which will be rendering it to showcase it in a table or some other information. Similarly, there are other API endpoints like the post, put, and delete, which you have to implement. So those are missing. So I'll show you briefly of what those API endpoints are also. So, but before that, so how you can run this server.js. So it usually runs on the localhost 80. So if you run npm start or node server.js, so it will run on the localhost 80 port number. And this is within this app.listen. So you can change the port number also to which port ever you want to use it. So this is the public and the views, which we are not covering. So it's just the front end part. So that's where I don't explain all this front end, how the CSS and the JavaScript are rendered on the front end side. So now how you can run the application. So you can download the provided application from the Moodle or from the server, which I think you should already have the credentials for logging into it. So then you can run it on a virtual machine or on your local laptop by unzipping the zip file. Either you can use the unzip or some other program for unzipping it. Then start the MongoDB. So for starting the MongoDB, you have to create a directory file where your all the data would be stored of the MongoDB. So this is like make directory and then specify it as a DB path within the MongoDB command line parameter. And for starting the Node.js application, first you have to run the npm install for installing all the dependencies, and then npm start or node server.js, which is the main file. And point to note over here that I'm using the sudo. So sudo is because by default operating system doesn't allow you to run any application on port 80. So it requires a sudo access. So that's why this is the sudo over here. And this is the front end side of the application, which you would see in the browser if you go to localhost 80. And now the last thing which you have to do is tasks which you have to complete. The first thing is the API endpoint, which is missing. So you can see this API endpoint is just documenting all the API endpoints which you have in the application. So currently we are only hard coding it, but there are certain tools like Swagger, etc., which can be used. But as part of this exercise, you just have to put this information over there. So this is currently missing. The next one is the API profile. So the API profile tells you to fill some information like name, home country, degree program, etc. So just fill this information. It's a static information. So you have to complete this also. Then the other three APIs which are connected with the database, one of them is the post request. So if you submit from the front end any book information, so you have to implement how should it store in the back end. So this part is missing over here. So you can see you will get the data from the front end within the request.body. So this will have all the JSON file required for storing in the back end. So now you have to write the code over here to insert it into the database using the Mongoose query. Similarly, the put request, put is used for updating the book information. So if I want to change the name or the author of the book, so you will get the ID of the book over here plus the body of the updated information. And lastly, the delete. So delete is for deleting the book based on the book ID. So now how you can submit this exercise. So I think you should all have the access credentials for the logging server, right? If anyone is missing who doesn't have the credentials, okay, that's good. So now you should first open the Cloud Class server URL, then log in with your credentials, then check the exercise 1, and then you have to specify the IP address of the application, where IP address of the virtual machine where your application is running. So now I have explained like the process of running the application. So you have to run this application on a virtual machine, and this virtual machine you can create within the AWS, Google Cloud, or on Microsoft Azure Cloud. So I'll not go into the details of how those VMs can be created. So as part of this presentation, you would find the slides for all 3 cloud providers, GCP, AWS, and Microsoft Azure. So it's very simple. Just from the URL, you can choose which virtual machine you want to use and all that stuff. For GCP specific, you have to use this link which I posted on the Moodle to get the credits. So you don't use your own credits. And once you have it, then you will go into the compute engine, virtual machine instances. So where you will create a new instance, which virtual machine. And then you would specify certain information like some name, which region you want to run this virtual machine in, how many cores or the memory this virtual machine should have, like over here. So I'm specifying the one virtual CPUs and 1.7 GB of memory. The important point to note over here is the Ubuntu, so Linux image which I'm using over here. So it's Ubuntu. So check this out also when it's creating the virtual machine. And another important point here is to allow HTTP traffic. So HTTP by default runs on the port 80. So if your application is running on port 80, so it will be allowed to access from the outside also. And so once you do that and then click on the create, so then you will have the virtual machine running in the Google Cloud. So once you have it, then you can SSH inside it. Does anyone doesn't know how to SSH, or everyone knows how to SSH into the virtual machine? Okay, so that's a good thing. But from the Google Cloud, it's quite easy. So there is an option over here to directly through the user interface only you can SSH inside the virtual machine. And once you run the application on that virtual machine, following the 2 processes, starting the MongoDB and starting the application, then you would see an interface like this on your virtual machine public IP with at the port number 18. And this would be the completed version of it, where you can see all the books information. You can delete, edit any book within the application. And for submitting, you have to submit the virtual machine public IP into the URL of the Cloud Class server. Yeah, so these are few links. So like you can use the GitLab at LRZ for code storing. And also you can use the WebStorm for the editor or Visual Studio Code, whichever you prefer. And there is a nice YouTube video for Node.js introduction. So yeah, so that's all from my side. Does anyone have any questions? Yeah.
Is there any reason to not use AWS?
So the question is there any reason not to use AWS? So there is no particular reason. So AWS, so because we have the Google Cloud credits, so that's why I showed you only the Google Cloud. But as part of the presentation, there are this AWS VM creation is also there. So you can check if you prefer AWS, you can use that also. Yeah. So the question is, where can I find the credentials for logging into the server? So you can find on the Moodle for your specific group. So there would be a post in the Moodle for your specific group, that credentials for logging into the server. Any other question? Yeah. Yeah, so with the AWS Educate, I think they recently removed giving the credits. So now they only push you to the Educate account where they have their own tutorial and stuff like that. So they have removed the option of giving the credits. So I would suggest you to prefer than Google Cloud. Any other? Yeah, then that's all. Thank you.
Welcome.